Like I've already been introduced, I'm Dr. Srikant Srinivasan, and I'm an associate professor at IIT Mandi in Himachal Pradesh. And my email ID is at the bottom over here. And I'm thankful to the Rajiv Gandhi National Institute of Youth Development and NIT Jalandhar, both for giving me the opportunity to connect with students. So I thought that I'll discuss about the application of data science in agriculture. The data science and machine learning itself has become a very hot topic, and there is really no need to elaborate further on the importance of it. In fact, all the IITs are now starting undergraduate degree programs in data science, which even IIT Mandi has started. So the machine learning and data science aspect is becoming very important, and it is something that is almost going to become as commonplace as the learning of some linguistics. Like if you know English, if you want to progress in science, you have to be well versed in English. You're just going to be well versed in data science in future. This is something that's going to percolate down. But beyond all the mathematics and the logic associated with data science, it is also very important to understand how it is very domain dependent. In whichever domain you have to know the domain you are going to work in quite well in order to put data science to good use. So this is why I wanted to talk about the application of data science in agriculture. We are at the IIT Mandi campus. Just move this aside. Okay. So this is our IIT Mandi campus. I'm currently situated on here. This is where I'm giving my talk from. And then we have the South campus, which are both separated by a hill. So we have this very nice, lush green surrounding areas where we are able to very peacefully conduct our research and take long hikes and walks. And of course, while there is all this peace in our surroundings, there are also big problems in the world, and the important one is that of the food security. So according to the United Nations Food and Agricultural Organization, by the year 2050, the world's population will reach about 9.1 billion. That means 30% more than what it is today. And nearly most of this increase will occur in developing countries. The annual cereal production, that means your grains and rice and wheat, all of these pulses, will need to rise by about 3 billion tons. So proportionally, right? From 2 billion to 3 billion, so you're increasing it by 30% again. Studies estimate that the aggregate negative impact of climate change because of the global climate changing patterns, for example, on African agricultural output could be between 15 and 30%. So population is increasing. The increase is going to happen mostly in developing countries. We need to increase the food production. And yet at the same time, we have been informed that the effect of climate change in recent times is to reduce the agricultural output. So this is a serious issue of world food security. And we have to see how can we, apply the knowledge of engineering and data sciences to improve this. So one of the first things people did is trying to go into high throughput breeding. That means you're trying to come up with various plant varieties that can give you good yield. For example, on the figure on the left side, you can see there are 3 maize plants. And if you take the one on the left and one on the right and you cross them together, this is called a hybrid. And that's what you get in the middle. And what you notice is that if the one on the left, which is labeled B73, and the one on the right is labeled as MO17, if they are hybridized, the output is like much higher, right? So this is something which is now widely accepted, and since hybridization of plants, there's been a lot of increase in food production. Of course, there are lots of people who are opposed to this on the basis of organic farming and all. I'm not getting to that discussion. I'm trying to make a point here that people are trying to trying to find out various ways to improve the food production. And they are basically trying to come up with new varieties which can improve the yield. This is what we talked about the green revolution in India and all of that. But what's interesting is, if you actually characterize the plant just beyond the yield, right? We are only looking at how much output is coming. But if you look at the plant behavior itself, it's very interesting. If you see different varieties of plants like A, B, C, D, E, these are all maize plants, corn plants, right? Which you're seeing on the left side. but you're taking a top view image. So normally these plants are about 6 feet high, 7 feet high. When you walk into the field, you don't see the top of the plant. The plant is taller than you. But if you actually went above the plant and looked down, it's very interesting that different varieties of plants exhibit different patterns. So if you see the plant number D, all the plants are like arranging themselves so that the reception of sunlight is maximized. If you look at some of the plants like A, B, and C, then they are randomly organized. If you look at the plants in E, then they are perpendicularly organized. So when you're actually hybridizing or creating new varieties, in addition to the yield, you're also affecting various other traits in the plant. And what might be of scientific value is to know that how each of these traits is actually affecting the final yield output, because that can help somebody understand that depending on which region I'm living in, supposing I'm living in a mountainous region where there is a lot of shade and shadows, like what I showed in my IIT Mandi figure here, and I'm growing some crops in some shady region, maybe I need to choose the right varieties which can best adapt themselves to the direction of sunlight. Whereas if I'm growing in some plain region or I'm in Punjab or somewhere, then I really don't need to worry which variety. I could have variety A or B because it'll have sunlight from all directions. So the point is that when we want, this is where the data science comes into play. When you want to understand geographically, according to different climate types, different regions, what is the best way to grow crops, you need to collect a lot of data. So here is another example that, I've called the slide techniques of big data analysis. If you see like the top part of the corn plant or the maize plant, this is called a tassel. This is where all the pollen comes out. Okay. So if there is a lot of pollen, that means you have a lot of yield. So what you can do is, if you have these image processing techniques, then you can automatically estimate across different varieties what is going to be the potential yield. And beyond this, you can also have various other traits. So what I've drawn here is called a heat map. I'm not sure if you're all familiar with the terminology. And what this heat map tells you is, it gives you these patches. So something which is like bluish has low correlation, something which is green and then heading towards red has high correlation. So on the x-axis, where I've written genotypes, that actually refers to having varieties. Genotypes means varieties. So if I have like about thousands of varieties of plants of the same thing, these are thousands of varieties of maize plants, and I measure the various parameters for each of them, like the leaf angle, the size of the tassel, the length of the tassel, the number of spikes, what is the height of the plant. If I do some NIR spectroscopy, that is near infrared, then how much starch content is there, what is the width of the leaf, how long does it take to reach flowering stage, and in the corn itself, how many kernels are there. So all of these are various characteristics. So this is a data set, right? This is a big data set. You have thousands of varieties, and for each one, you're measuring these various traits. And clearly, this is an experiment that was carried out over a long period of time by many people contributing to just get this one data set. But once you have this data set, using a heat map, that is finding a correlation analysis, you can quickly tell what is the, how different genotypes are related to each other and what are the different traits that are related to each other. Now you may ask, what is the purpose of all these traits, right? Why do I need to know all this? After all, I have only one interest, how to get good yield. I want to get a lot of output. Well, you see, the problem is that when you're growing a plant, the maize plant, for example, takes 3 months to grow. You know the yield only after 3 months. And supposing after 3 months, I don't have enough yield, it's too late for me to do anything. There is no food. So I have to be able to predict the yield. I have to be able to know beforehand, is this a successful strategy for me or not? Therefore, when you have these many traits that I have shown on the right side over here, if these traits are correlated with yield, then even when the plant is growing at a young stage, based on the leaf width, the leaf length, or based on some other trait which may be correlated with the yield, I can predict that 2 months down the line, what is going to happen to this plant. Now, this is where we are doing some predictive analysis, and the prediction requires that you have to find the appropriate traits, which I've written here, which are correlated with the feature of interest. So for you, for us, it may be yield, or it may be the leaf shape, or something that some scientist is doing. So the point is that when you're working as a data scientist, you're not only going to be able to handle the data, if you want to get meaningful information out of the data, you have to get into the domain itself. You have to know where exactly your application domain is and what exactly is it that you can do to contribute to it. So as a computer science student, you may learn about correlation analysis, statistics, heat maps. You may learn about linear regressions or various other kinds of regressions, deep learning and all of that. But in the end of the day, you have to keep your eye open on the domain so that you know where is it that you're going to apply this and where it is that your particular technique can contribute. So here, for example, are just another scatter plot matrix of various traits. And you can see that there are traits on the x-axis and y-axis and how they correlate. For example, this one would be, this figure here is something that has very low correlation, right? Because it's almost a straight line. Remember, a correlation plot means I have some variable on the x-axis, I have some variable on the y-axis. If they are both correlated, that means they are related to each other, then I'll get a line which is like this. That means for any small change in x, there is a change in y. So they are both progressing together. For example, if you take height and weight, right? So height of a person and weight of a person. Normally, as the person becomes taller and taller, his weight will also increase. So that's like a correlation plot. So this plot over here is showing that the x-axis is changing, but the y-axis is not changing. That means these traits don't have any relationship. Whereas if you look at some other traits like this one, then you can see that there is some correlation. As the x value is changing, the y value is also changing, but there is a lot of noise. So then you have to think about finding statistical descriptions to describe this data set. And this way you find out which traits are of importance to you. And then you have to be able to measure those traits in advance to figure out what is the yield of your plant in future. So, for example, corn is used in various, products. So beyond food, beyond the popcorn that we know, it's also used as a sweetener. It's used as cornstarch. It's used in cellulose as your, the capsule material. It's also used for fuel, right? Because they're making biofuel and all that. Now, while we are doing all this variety improvements in the corn itself, we are trying to come up with new varieties. The problem is, in the end of the day, whatever gains you're getting, that's this plot over here. This plot is showing the y-axis is the yield, x-axis is the time. So you can see from the 1800s to the 2000s, as the decades have progressed, the yield has increased, right? Food production has increased, but then there are huge dips once in a while. Why are these dips there? It's because of weather events. So even if you have good science, in the end of the day, the weather itself can affect your plant drastically, and then all of that goes to waste. So there are two features you have to tackle. One is the inherent behavior of the plant, and then its response to the environment. So there are now two things that you have to keep under control. So let's look at the challenges of Indian agriculture. So this data set which I'm showing you, for example, shows Iowa corn yield, and some of this is US data because I worked in the US. But now let's look at the challenges of Indian agriculture. So agricultural growth rate has reduced to 1.7%. This is from the Food and Agricultural Organization. But my slide may be a couple of years old, so it's possible that now it's not so bad. But some of these are serious problems. Land degradation, for example, is a major threat to India's food security. You can see that about 30% of the blocks in the country report that groundwater has gone to unsustainable levels, and large tracts of farmland have become barren due to imbalanced fertilizer use and excessive use. Why does this happen? Because of these weather problems. Because a farmer, finally, he has to earn his livelihood. And when he sees that these kinds of issues are happening, he wants to play safe. So he throws in as much as possible fertilizer, urea, and sprays with a lot of pesticide because he has to ensure his livelihood. But you see, because he doesn't have the appropriate information, this is actually leading to long-term degradation of the land. And therefore, there's a need for precision agriculture, which is like a decision support system. So for the whole farm management, so that you can optimize the returns on the inputs while preserving resources. So you're minimizing your input cost, maximizing your output benefit, and protecting the natural resources. Precision agriculture requires you to relate the productivity with geography, environment, water, fertilizer. So the plant's inherent nature, what is going on inside the ground, what is above the ground, and the general geography of the area where you are. Then precision agriculture can help you can tell you whether, give you early warnings of whether there are some stresses like due to water or some lack of nutrition, or if there are effects of disease. Then comparing multiple varieties to determine the ideal region specific variety, determine the best practices in farming, including crop rotation, and then data acquisition to build machine learning models to fill these kind of gaps. So the important thing is good data analytics requires good data. This is a very, very key point. Normally, most data scientists, at least when you're starting to train as a data scientist, one thinks that it's all about the algorithms. But very quickly, you find out that everybody knows algorithms, but very few people have access to data. So a big challenge is how do you get good data, reliable data, that puts you ahead of other data scientists. So in the case of agriculture, for example, the methods of phenotyping in the US include using tractor kind of machines which are retrofitted with various sensors. So you have a GPS which tells you the location of the plant. Then for each location, you find out based on different sensors what is the growth of the plant or different parameters that you're measuring. And then you have a data logger system that takes the GPS value and the sensor value, puts it together, and then you have data. The problem with such heavy systems is that, if you keep running them, then the soil will get affected over a period of time. So this is not something that is very useful in our context. And the second thing is Indian farmers have very small land, like 1 or 2 hectares maximum, 1 or 2 acres maximum. Whereas in the US, average farmer has like hundreds of acres. So for him, it makes sense to have huge machines which cover huge land. We have a lot of people and less land. I mean, we have more land, but we have a lot of people having small pieces of land. So for each person, it's not at all feasible to have some solution like this. We have to come up with cost-effective methods of solving this problem. So some of the work we've been doing at IIT Mandi, we've started off with the use of UAV drones, where we've worked with quadcopter and hexacopter. So this is a hexacopter. Hexa means 6, quad means 4. So a quadcopter is a UAV which has 4 blades, and a hexacopter is something which has 6 arms. So there is 1, 2, 3, 4, 5, 6 arms. So this is a hexacopter drone, and this is the ground station, and it can be fitted with a camera. And on top there is a GPS unit. So this is developed by my PhD student, Mr. Joe Johnson, and he's been using this to fly over various fields and do some measurements. So with the UAV, then the way it works is, the UAV system is going to fly above the ground, and we are going to basically have to see what is the health of the various crops. And let me start by, let's see how to get this going. Okay, so here is a video. I'm not sure if the video will play to you, but let's play it. So this is a video of a UAV flying over the ground. These are various corn plants, and the corn plants have, these are different varieties of corn. You can see that there is a lot of challenge, because when we conceptualize a UAV, we think it's just flying very smoothly, but this is what a real UAV is like. It's flying, it's going up and down, it's getting buffeted by the winds. We want to measure, say, tassels or the flower regions. And you can see that if the UAV gets too close, the plant starts getting blown away. So you cannot get good imagery. If you go a little, above, or if you try to hover slowly, then the winds keep moving it around. And it's difficult to get a good read on the data. So these are like, huge challenges if you want to use something like a UAV for precision agriculture. So precision agriculture means you want to go very close to the plant and see what's going on. So clearly UAV is a big challenge for doing something like this. Yeah. On the other hand, a UAV is very useful if you want to go at a much greater height. So if I want to do an average study, right? If I want to do a statistical study, not a plant level study, but statistically, if I want to see over a large area, what is the overall crop growth? Can I measure the total green content? Can I measure certain parameters using different kinds of cameras? So what you see on the right side is called a multispectral camera. Left side is a RGB camera, like what you have on your cell phone. The right side camera is able to capture other spectra of light and which give different information about the plant, like its water content, whether it's healthy or not. So the UAV cameras can then fly over a field and quickly find out over large areas, is there a problem or not? How is this useful to a farmer? Because, after all, a farmer is not going to buy a UAV of 1 lakh. The advantage is that if you are in these regions where Indian farmers have small plots of land, they can form cooperatives. Then it's easy for, say, within an FPO, like a farmer producer organization, to have one of these and quickly fly over the field and get an estimate of, what is the potential yield that is coming up for that region. So that farmer can then know how much he's going to get and, bargain his market prices. So UAVs are very efficient and mobile platform for coverage of large or medium-sized field, but not for precision agriculture, but for large areas. And we've collected images from multiple locations. And of course, the challenges are the weight of the UAV, the flight time, because it's powered by a battery, it can run for, say, 25 minutes. And then in the mountainous terrain in Himachal, of course, we face the problem of GPS signals, and then lots of wind again in the mountainous regions. It's very useful for the plains. It's a very good option, but in the mountain, it can get a little challenging. But using some deep learning algorithms, what we did is, after doing a multispectral imagery, we took these images on the left side and we trained them. I'm not going into the details of it because that itself is an entire talk, and I think a talk, and somebody else is doing that on deep learning. But we fed this into a deep learning algorithm collecting all these images. And this is also a very painful task in the sense that you have to annotate the data. So you have to first take these images and create blocks and label them. Like the crop of interest for us was potato. And now other than potato, there are other things. So you have to label them. And once we did all of that, we trained the algorithm. And now if when we gave an input image, so this is a real example. This image is not labeled. It's a blank image. I fed it to the deep learning algorithm. It reconstructed it back for me by labeling it, and I've blown it up. And it's showing, for example, that if there was a patch over here in this image, which is somewhere around here, so this patch over here, that's kind of blown up over here. And you can see that it's captured that there is a pumpkin patch over there in the middle. And then it knows that here is potato. And on this side, there is grass. And it calls these regions as disease. You can see the quality of the leaves. They are not very good. So it may not be disease. It could just be due to stress, water stress or something. But we didn't go into the fine details. We labeled as maybe not disease. We should call it unhealthy. So there is healthy potato. There is unhealthy potato. There are pumpkin patches. And then there is just grass. Grass is basically what is neither potato nor pumpkin. We don't know what it is. So we think it's some weed and it's grass. So this kind of automatic analysis then speeds up things very much. And the main advantage of a UAV is you're seeing things from above the ground. Because when you walk into the field, you'll never notice any of this. You'll never know that there is a patch that looks like this or a patch that looks like this. Because everything is very dense. But when you have an aerial view, you're able to quickly figure out if there are big problems in a certain field. Like if there is a spread of disease, and you can see the spatial patterns of the diseases. The second thing we did is, like, for farm level data collection, we needed to come up with inexpensive weather station sensors. Right now in India, the weather data you're getting, for example, from the Indian Meteorological Department, IMD, it has, say, about 500 or 1,000 stations all over India. And that means, the weather you're getting is interpolated. You're having in the entire Indian map of India, you're having, say, 1,000 weather stations. And if you're somewhere in between these weather stations, you have to take some kind of linear interpolation of some method like that. The problem with agriculture is plants are very specific, are very sensitive to the environment. And we did a case study. So we developed these low-cost weather stations ourselves at IIT Mandi. These are solar powered. So there is no need of, and this is very important for agriculture because you cannot have cables and all lying in the ground because that will will get cut or it can hurt somebody. So we have a completely standalone solar powered weather station, and it picks data and then it transmits it wirelessly. So we put some of these weather stations around IIT Mandi campus within a 3-kilometer area because we are in a hilly terrain. So we wanted to see within these different regions, how much is the spatial variation. And that's what you see in this plot over here. So you see how this temperature is like fluctuating, because each of these lines is representing one weather station. So you can see that some area which is within a shaded region doesn't show so much variation. Some area which is in a slightly sunny or open region shows a very high variation. So depending on where you are located on the mountainous region, your crop within a very small distance is going to experience a very different terrain. And this kind of variation is going to clearly affect your agricultural output. So it's very important that if we want to do good prediction of data or good analysis, we need to have very good data in the first place. And good quality data means we have to come up with low cost systems which are able to reliably capture data. Because if you have to go into high cost systems, then Indian farmers cannot afford it. So the data collection part becomes very tricky. Now, if you're going with low cost, of course, there is no free lunch. That means there is going to be some problem, like maybe the sensitivity of the sensors or their reliability may not be very good. And this is where the data scientist comes in, because the beauty of it is now whatever shortcomings are there in the hardware, you can solve using software. So by coming up with appropriate algorithms, or say some kind of cubic spline interpolation, or some techniques that we have, various machine learning techniques are there, regression techniques, you can come up with very good fits for this. And what you can do is, if supposing I have a region of 1 acre, I can always take these weather stations and put them there for say a period of few months. I can correlate the weather station temperature with the IMD, Indian Meteorological Department. And thereafter, once I have found a proper correlation, I can remove these weather stations. I can now use the global weather station to figure out what is the local weather. You see, so now we have used data science to figure out what is the local weather pattern, although we don't have a real-time reading of that region. So that's a way in which we can use data science into this domain. If I want to go one step further, to this weather station, I can also add a fixed stationary camera. Here is an example of something we did. We added a camera, and let me see if I can play this. Yeah. So, excuse me. On the left side, you see plants which are emerging from the ground. The right side is the same image. I have done image processing. Okay. So I have eliminated the entire background using image processing by transforming to a different color space. And now I'm directly measuring only the plant traits. I'm measuring what is the volume of the plant or how much pixel area is covered by the plant. So you can see that number is being reflected on the box over here. So as the plant is growing, I'm able to count what is the total pixel area of the plant. And using this, I can basically not only now find out the weather of the region, I am also able to correlate the plant height and biomass, or more importantly, this is I could have correlated the plant height and biomass with temperature, or some weather parameter, environment. Let's call it environment. So I could have plotted some environmental parameters on the y-axis and then correlated it with the plant height. So now I have a very precise value of how the plant responds to the environment. So now I can grow many varieties in this region. I can grow multiple varieties of plants. I can have these weather stations. Using the weather station, I can figure out what is the local climate. Using the cameras, I can figure out what is the response of the plant to the climate. And then using data science, I can correlate the growth of the plant with the local climate, and I can correlate the local climate with the reading of the global IMD weather station. So finally, if I'm able to create these models, then wherever the farmer is in, now just using the IMD weather data, he can directly predict what is going to be his yield in the future. But again, these are all very challenging problems. There is still a lot of work to do in these areas. And again, it's very region specific. So there is a lot of physical effort required to go to each place, find out those parameters, and then correlate it with the weather pattern. So this is where we have to somehow make the farmers involved in the process, make them get us data. And this is something I'll talk about a little later. So let's go to the, some other examples. So here is based on the image data, we are able to capture the tassel of the maize plants, and then using again different kinds of machine learning processes. So these boxes which are not drawn by hand. They are automatically done using a deep learning algorithm. So when I feed these images to the plant, it automatically, when I feed the images to the computer, the deep learning algorithm automatically places these boxes very tightly around these tassels. And using that, we are then able to extract the tassel traits. So see, even this has become very automated. Imagine if you had to do this in the field manually. Somebody has to go with an inch tape and measure all these things. It's going to be very cumbersome and prone to errors. But when you make this process automatic, then you get these values in a very reliable fashion, and you are able to generate a high volume of data, which is very important to us as a data scientist, because we rely heavily on statistical models, and for statistical models, we need a high volume of data. So this is also something that's very useful when you automate the procedure. So this is something we had published a couple of years ago. Now, based on all this, of course, this is me standing in our model field. So we've put up these poles where we've now attached these various weather stations. So each of these box carries a Raspberry Pi microcomputer. A Raspberry Pi is something I hope you're all familiar with. So nowadays, the IoT, Internet of Things domain has been flooded with various low-cost microcontrollers like Arduinos, Raspberry Pis, BeagleBone boards. And these are all microcontrollers which allow you to do small operations. So I have a Raspberry Pi which is connected to a camera. The camera is imaging the field. I have a variety of crops grown here. The experiment we are conducting here is that for the benefit of local farmers, can we find out what varieties of crops can be grown that are commercially viable, that is good cash crops, but are not known to the people indigenously. So normally people are historically growing some set of crops which is not fetching them good value, and therefore they are not getting good benefit out of it, good market value out of it. So our interest is to see, can we introduce different varieties that are that can respond well to the local environment and fetch good market prices for the farmers. So that's what we have done here, various plots. And then we have these poles with the cameras and sensors and all of that, and we're doing this precision measurement. Now, you see, there is another problem. I talked about the fact that automation makes things easy. We are able to get a lot of data and all of this. But just think about it. Each of these cameras, supposing it's snapping an image every 15-20 minutes. So I have about 50 images a day. And if I have many cameras like this on the small field, I'll very soon be generating gigabytes of data. How do I go about collecting this data? Can I actually go to the field and plug a USB stick to every one and keep collecting data? That itself is going to be a full day process. So very quickly, there is the issue of, a clogging of data now. We have got so much data that how do I access the data? The second problem is, if I have many of these sensors, how do I know if something has failed? Can I go physically to everyone and see, is this working? Supposing the camera is clicking once in 20 minutes. Then what am I going to do? Am I going to wait there for 20 minutes to see is the camera turning on and snapping an image? And then there are so many cameras in the field. So how do I deal with all of this? So this is where the Internet of Things comes into play. So this is called a cyber physical system. The cyber system is of course, the internet part. The physical system is the physical components that you're seeing on the field. So when you integrate all of this, then what can happen is you as a remote person can be sitting somewhere and have access to an HTML server. And through that, on the field, what's happening is every Raspberry Pi is connected to various cameras and sensors, pulling data, and that's connected to some server. And then you are directly accessing the server from some remote place. So this way you're automating the entire process. You're able to pull data in real time. In real time, you're able to monitor the field. You're not only able to monitor the crops, you're able to monitor the health of your equipment. Are they working or not? So you know exactly where is the problem. So there is a lot of engineering involved over here, and there is a lot of data science involved in just the engineering part of it, even beyond the domain. So the data science of the domain is how you apply data analytics to the plants. But you have to apply basic data analytics even to your equipment to understand what is the reliability of your system, whether it's working well. Is there some what is the rate of power consumption? Supposing this is all running by battery with a solar panel, I have to track at what rate is my battery getting discharged, so that I know, if there's going to be a problem or if certain batteries are not working well. So as you get into the domain, the data science application becomes ubiquitous. You have to use it in every possible way to ensure the reliability of your system. So this is something we then set up in different villages in Himachal Pradesh. So this is called Mandi village, Salgi village, different places, same systems, and bringing in the local population, trying to get them interested in this, because these are all physically taxing jobs which we as faculty and students cannot handle. So we have to somehow get the local population integrated into this, to get them interested in this, to help them see the benefit of it, so that they can take the ownership and responsibility, and checking for the maintenance of it. So this is where there's a lot of social component also in ensuring that the system is working properly. So this is the part which is about the farm level data collection. And then one of the things we have developed actually is we have collected images of potato leaves from various places, Punjab, Himachal Pradesh, UP and all. And using that, we built another deep learning model using color space transformations. And we have come up with an automatic blight diagnosis. So blight is a disease in potato which basically wipes out the entire crops within a few weeks. So if this is not caught on the right time, a farmer can completely lose his field. So we have come up with some algorithms which are then able to, you can see the numbers here. So with about 99 to 98 to 99% accuracy, we are able to capture when there is a disease in the plant in an automated manner. So this is like the image. So this is a sample input image. And then we have a detection model which draws these bounding boxes directly on the blight patches. And it's telling you with reasonable accuracy that there is blight. You see, the challenge in this image is that if you see these patches, you know that on potato leaf there is a patch and there is a disease. But the computer, it sees this patch and it sees the background soil patch and it thinks they are the same. So there are a lot of challenges in this. Like when we initially started doing this classification, we had a two-class model. This is called a two-class model. That means it's either disease or no disease. And we noticed that the algorithm was many times mistaking the background soil for disease. So then we created a four-class model where we trained the algorithm to know that this is a leaf. Only if you see a patch within the leaf, it's disease. So if you see a patch outside the leaf, it's not disease. So that way we were able to teach it how to do soil patch, distinguish between soil patch and distinguish between disease patch. And based on that, then we got this very high accuracy of disease detection. So these are some of the things that we have done in the context of precision agriculture. Now, what I want to talk about in the second part of this talk is about farmer zone, and briefly I'll talk about it. The main thing is, in the first part of the talk, whatever I discussed so far, which I gave you a broad overview of agriculture and the use of data analytics and data science. This has got to do with us as data scientists or engineers, separated from the farmers. We are not actually talking to farmers. We are basically just engineers or scientists who are gathering data, analyzing data, developing engineering systems, solving problems. The second part of the problem is, how do you actually deliver value to the end customer, which is your farmer, right? So as engineers, all the science is fun for us. We have developed all these systems, we are doing things, we are learning things, we are getting our jobs. The second thing is, how do we deliver value with our knowledge to the end farmers who may know nothing about machine learning or data science? How do we get them engaged in this process, right? So let me pause briefly and again ask if there are any questions. Yeah, I saw one question that flashed. Can we use these methods in Indian agriculture? So some of the methods that I've shown cannot be used so easily in Indian agriculture, like the big tractor kind of systems. The first question is, are these methods applicable to Indian farms? So anything which is expensive is not applicable to Indian farms. That's the bottom line. No Indian farmer is going to be willing to invest money in any of these systems. Who will then buy these systems? So there are different categories of systems. There are systems which are cheap and affordable that can be bought by farmers. For example, smartphones, right? Smartphones, we did a survey of various farmers, and I'll talk about that in the farmer zone part of the talk. And lots of the farmers have smartphones, not because they care about agriculture, but it's the hot thing, right? So even if the farmer has a lot of financial problem, the farmer or his son or somebody ends up buying a smartphone. So they all have a smartphone. If I develop a mobile app for a smartphone, a farmer is willing to use it. If I buy a UAV system, is the farmer willing to use it? Not an individual farmer, but now there are lots of progressive cooperatives who are willing to invest in such systems. But beyond the farmer himself, right? When we think about, we are delivering value to the farmer, but exactly, big producers like Lay's and ITC and all have these systems. So this is what I was getting to. that the end farmer himself does not have much monetary strength or power to invest in such things. But there are lots of insurance companies, seed producers, big seed companies which are now awarding farmers these contracts so that the farmers grow the company seeds and then sell the produce back to the companies. So the companies are basically outsourcing their large-scale production to farmers. These companies can afford such systems, so they use such systems to check whether the things are working well or not. It also the companies use it for another reason, because when the companies do contract farming with the farmers, sometimes what happens is the farmers, once they get the contract, they don't care, because sometimes they tend to become lazy. They don't deliver. They'll take the money from the company, they'll take the seed from the company, then they'll not worry about taking care of the crop. So the company actually wants these systems to ensure that if I've written a contract with the farmer is actually adhering to the agreement. He's taking the proper care of the crops the way the agreement specifies. So there are various reasons why these people are interested. Insurance companies are interested because they want to know that what are the appropriate insurance rates that they should be offering, because based on the growth of the crops, if you can predict the yield, then the company also wants to know that what is the risk assessment to the insurance company. So there are lots of such players who are interested in investing in such kind of systems. At the farmer level, our experience has been that usually it's the cell phone, smartphone thing works best, because the farmers buy it. Whether we ask them or not, every farmer, at least 50% of the farmers have smartphones. And therefore, if you can get them interested and show them the value of having something like this, they are willing to adopt it. In which regions can what be used? So for example, if you're talking about the smartphone kind of system, we have demonstrated it in Punjab, Himachal Pradesh, Uttar Pradesh. We are now building initial links with farmers. We've registering a sample set of say 100 to 200 farmers in Gujarat and in West Bengal. So because we are in Himachal Pradesh, geographically it's been easy for us to expand in this manner. And later on, we are thinking about other like for other crop types like rice or other things in South India. But there are many other issues associated with it that we need to first understand clearly before jumping into that space. So let me talk about the farmer zone, which how far is the experience? So the experience with the farmers is that normally if you are having this smartphone kind of system, which is, see, mostly farmers are, okay, so let me talk about farmer zone. The questions you're asking about the farmer is all going to be addressed in this part of the talk. Okay, so this is about delivering value for the farmers. And then if I don't address any of those, we'll take it up. So Farmer Zone then was a project that was started at IIT Mandi. The secretary of the Department of Biotechnology was visiting IIT Mandi at that time. And I happened to chat with him and somehow it clicked very well. And then we got together and along with various other, entities, academic and government entities, and came up with this project of Farmer Zone. So what is Farmer Zone? I'm trying to now get this out of my screen again. Okay, thank God. So Farmer Zone is Department of Biotechnology's vision for a cloud service, a collective open source data platform for smart agriculture, which is a, something that's like a big boon for data scientists. Whenever you see a collective open source data platform, it's something that should make all data scientists happy. It's for dissemination of farm level information. This is very important because we are talking about getting precise analytics to farmers at the level of their farms. And then a platform for collecting, curating, and analyzing data and distributing it as need-based solutions. So collection of data is what I discussed with you all this time. And then curation of data means how do you ensure the integrity of the data, that there are no missing data, gaps, how do you fill all of that? And then analysis of data is all the machine learning and the fun part. Then finally, the services will be that for the farmers, we can give them weather prediction so they know when to plant their crops, when to harvest the crops, giving them advice on irrigation and soil nutrition, and then advanced detection of diseases like what I showed you with the potato disease detection app, and then market information, because this is very important. As engineers, the part we are, or scientists, the part we are comfortable with is usually the developing of systems and how to improve the productivity of the crops. But what we are not very comfortable with normally is what happens after the crops are grown and harvested? How do they go to the market, and are they actually bringing value to the farmers? So that's something also that's a mandate of Farmer Zone. And this is why I'll then talk about the farmer's experience, like the question you asked, Lokesh. So the idea of the Farmer Zone platform is that you are going to have sources of data, say from the public and private entities. I have not drawn private over here, but public entities like IMD, ISRO, and NABARD, which is the National Rural Development Bank. And then how do you curate the data and do all of that? Then storage of data on cloud systems, which are public data utilities. Then this data is fed to agri supply companies or agri universities experts like the Krishi Vigyan Kendriyas, KVKs. These are all, extension units set up to help farmers. So farmers may directly not, connect to AI system or some Google Cloud or something to figure things out. But these intermediate persons who are educated and who lie between data scientists and farmers may be the right customers for us. So they will be able to get the value out of the system and then deliver it to the farmers in a way that is beneficial for them. So then finally, the other thing is from the farmers itself, we have to collect a lot of raw data, and that also comes in. So we have data from government sources, we have data from private sources, which is not written here. I should have put it. And then collection of data from farmers, then doing all the data analysis, the curation of the data and denoising and all of that, doing the machine learning, giving the advisories. Advisories can go directly to farmers, or it can go to these various supply companies, universities, experts, and startups. Okay. The objectives are then to collate agri data from national and international resources, region-specific crop forecasting algorithms. This is a big thing for us. Develop models of public-private partnership. The reason for that is some system that we are developing like this will not perpetually be funded by the government. So the government gives us money, say 10 crores initially. We have to make it self-sustaining after that. The government is not going to keep funding us perpetually. So what will happen is we have to somehow bring the customers into it. We have to bring the agri ecosystem into it, the various supply chain people, and deliver value to all of them as well, so that they are the people who can then take over the system, and it continues in a self-sustaining way. Not take over the system. It will be under the control of the government only. But these are all people who can actively participate in the system and make it run. It's not that the system is always relying on the government to pay for it. So that's also one of the mandates over here. So that's why we have this public-private partnership. Then models of farm-level data collection, real-time market information delivery system, weather and climate risk data models, then efficiency of information delivery to the farmers, including affordability and access. Then let me just close this for now. Models of cloud infrastructure, business models, and things like this. Okay, so now you can see that as a data scientist, there is a lot of things beyond just algorithms. You have to think about the entirety of the problem. How do you ensure that your solution is a viable solution beyond just the analytics that you're doing? How do you ensure that it is acceptable to society and it continues in a self-sustaining manner? So the Farmer Zone ecosystem started off with IIT Mandi as the lead partner. I am the principal investigator from IIT Mandi. And then we have domain experts like the Central Potato Research Institute and various other entities like Penn State University in the US. And then there are some institutes in the United Kingdom and some private companies. We also brought in certain, agri players like farmer producer organizations, seed companies. I have not mentioned it here. And then there is the entire architecture of the Farmer Zone. This is the backend on which everything rests. So we have the data coming in from the various sources: private data, government data, farmer data, and all of this then connects to the net and through various software models. So I'll not go into this detail. This is not my expertise, but some of our team members are working on all of this. The end of the day is all of this then connects to a certain web application that goes either as a mobile application to the farmer, or you connect to it as a browser, and different kinds of software chains through which data can get advisories can get disseminated to different interested parties. So in the beginning, we first, our clients are the farmers. So we created this farmer registration app where we had to bring in details of the farmers, their land detail, crop details, soil details and things like this. And at every stage, there is a lot of challenge. You have to have the right person to execute the task. For example, if you're going and talking to the farmer, then farmers are very skeptical about giving out their details, and because there are lots of connotations to this. For example, if the farmer tells you exactly how much money he's making and what are the land details, he may be afraid that maybe he's not paying tax or anything, and he doesn't want this information to go out. So reliable data science, I told you in the very beginning, good data analytics requires good data, and the challenge is how do you get good data. So how do you build trust in your client, and for them to be willing to give the data. And then the second thing is the security and privacy of data. If he's giving us the data, it becomes our responsibility to ensure that this data doesn't fall in the wrong hands. And wrong hands means anybody whom the farmer doesn't want. If the farmer says, I'm giving you data based on trust, then we cannot let it go into the hands of anybody else. So we have to ensure that there's proper security in the system and all of this. So, but that's a different topic. We'll not get into it. So we've then, basically registered lots of farmers. We went around talking about this farmer zone. So your question is, how do farmers receive it? Farmers are very curious people. They are very interested in, a lot of these kind of things, but their curiosity is also short-lived. If you do not deliver benefit in a palpable way in a short time, they quickly lose interest, and you cannot make them interested a second time. So this is a big challenge. So the first time, we talked to the farmers and we talked to them about various benefits. This is actually in Lahore region of Himachal Pradesh, and this is in Jalandhar and other places in Punjab. I think this may be Meerut in UP. So different places where we went to different farmer organizations. So we've hired about 10 field officers or 12 field officers who routinely travel on their motorbikes and go to different farms, talk to farmers and gradually get them interested. And then this way, the farmers are supposed to talk to their neighbors and it should propagate. So in the first set, we've registered about 5,000 farmers across 3 states. And we are using this as a test bed. These are farmers who are more progressive, and we want to see whether, they are thoroughly interested and are they getting benefit out of it. And if they get benefit out of it, they will automatically, talk about it to their neighbors and it will spread. So one of the things, like I told you, farmers are interested, but they're not willing to commit much time. So to get them interested in the program, what we did is we offered a free soil testing facility for them, and we went and sampled all the various soil patches of the various fields, and then we gave them some fertilizer recommendation and things like that. And there you can see that when you measure the soil, you can see all these various parameters like nitrogen, phosphorus, potassium, and all of this. The idea is that when you measure all these parameters, you are also creating your own data set, and you're creating a reliable data set. See, when you talk about farmers having soil health cards and all, we have heard of farmers coming and telling us, sir, the government mailed us a soil health card, although they never measured soil, took a soil sample from us. So, you hear these strange stories, whereas, in some cases they got, reliable data. But the problem is, as a data scientist, you want to have control over the data. So we thought we are solving 2 purposes here. First, we are collecting the data and we are offering a free service to the farmer, which makes him loyal to our program. And we are getting reliable data because we know we collected the data, we are measuring it, and therefore we can build reliable data models for what might be required for that region. And so we've actually created soil maps for different regions of the states, showing what is the requirements across different geographies. Then we developed the app for the delivery of advisories to the farmers. So I'll just go through it a little quickly. The idea is it started off in collaboration with a Penn State University, and now this app has changed considerably. It doesn't look like this anymore. It's a lot more intuitive. But in the these were the initial phases of it, where we then had to develop this potato AI artificial intelligence model, and we put it in different languages. So that was also a major challenge on how to get it onto. So this is Punjab, this is English, then there is Hindi, and then there is Punjabi. So we got it in 3 languages for the 3 states, and then basically we had to go to all these 5,000 farmers and explain to them how to use the app and take their feedback, because we wanted to know how they are perceiving it, what are the challenges they are getting it. Before you release it to a larger community, you want a test community. And therefore, we did a lot of in-depth feedback from the farmers to see how they perceive it. Are there problems being solved with it or not? So based on the various feedback we got from the farmers, we narrowed down on an initial set of deliverables. So the first was planting advice. That means farmers need to know when should we plant to ensure that we get good yield. The second is they need soil advice. Given a certain soil type, how do we know what is the right inputs to put and what is the minimum amount to put? We don't want to spend money buying lots of things, because normally what happens is these farmers go to the market. Somebody gives them some idea that, oh, you are in this, you want to grow this crop, you buy this. The shopkeeper himself is giving the idea. It's a conflict of interest, right? The shopkeeper is selling it to them and saying, you buy this, it will be good for you. So farmers want some independent advice on what is good for the soil. And then region specific advice. The POP stands for package of practices. So region specific advice on what is good for that region. Then weather based advice. That means if we are able to take, what I talked about with those sensors and the IMD weather data, can I do some weather prediction and tell them that this is when you should plant your sow your seeds. We tell them that if there is a lot of humidity, then this is a chance for disease to come. Remember, we built a disease detection model for the potato blight, but the blight detection model captures the disease after the disease has come. Can you predict the occurrence of the disease? And in fact, our collaborators from the Potato Research Institute have shown that certain combinations of temperature and humidity result in blight. So using this data, the localized farm data, we can tell a farmer in your local region, is there going to be a potential of disease coming up soon or not? If the farmer does not have this advice, a farmer, to play safe, what he does is he buys a huge amount of pesticide and he sprays the plants regularly. Every 3 weeks or 4 weeks, he sprays the plant. He loses a lot of money. The environment is degraded, and we as the end consumers are suffering because we don't know what's going into our plate, right? People are saying live healthy, live green, eat greens, and your greens have a lot of pesticide. So this is a big problem. So these are various ways in which you can have good impact. And then the health advice for the plants, and similarly disease advice. So for example, this is a planting advice. So it says that for a suitable date of planting, the temperature should be below 32 degrees. And this is a static advice, right? This is a model that I've built, and I'm telling you that the maximum temperature should be below 32 Celsius for the potato to flourish. I mean, for you to plant the potato. But now we have taken it to the next step. Now we have dynamic weather advice. That means you tell the farmer, just based on his GPS location, if he just clicks asking, can I plant now? The algorithm automatically goes to the database, finds out what was the weather for the previous 7 days, and tells the farmer, yes, plant or don't plant. So that's the more advanced stage of dynamic weather advisories. So then here are various other advice we have given them about the soil preparation, what varieties are suitable for the region, how to prepare the field, what is the source of seed, how to do the planting strategies, and various other things over here. Now, finally, there is some other screens and all. I guess there's no point in just going through screen by screen, but basically a lot of useful information for the farmers that we have put onto the app. And at some point, it might be like an overload of information. So that's where we need to actually talk to the farmers, and periodically get their feedback on what is useful for them or not. So this is the image detection app that we have integrated, the image detection algorithm. So I'm sorry, there's some noise coming from here. Somebody is doing some drilling work. Is it coming to you? Are you getting affected by it? What happens is we have given this pictorial representation for the farmer. This is a farmer from Punjab. So he can go to so this flashes on the screen of the farmer. So he knows that he has to stand close to the potato plant and then take an image. So we have built that into the app now. So when you actually take the phone to the plant and snap an image, in real time, using our app, it tells whether the disease is there or not. So that's a compressed deep learning model we have put there. So our deep learning model is now down to about 30 MB. So the original model we had built was like about half a gigabyte, and now we have brought it down by 10 times, and now it's like about 30 to 35 MB. And so now it's running on a smartphone comfortably, and then farmers can directly use it to find out what is the disease. The model was initially done so that when the model was big, it would run in the backend server. So farmer clicks an image and the image goes to the backend server. Now that we have compressed it, it's on the phone itself. So even if the farmer doesn't have internet connection, You can just click and then you can find out whether there is disease or not. Now, of course, we have to test this out in various areas and make sure that it's working before we distribute to the general public, because farmers lose trust easily. So if your model doesn't work, then they'll stop using your app completely just because one feature did not work. So this is why we are going through that beta phase, where we first make sure all our progressive farmers are using it and are they happy or not. So we have to run this over a couple of seasons to make sure across different soil conditions, different background conditions, different lighting conditions, this model is working. When we are sure about that, then we will release it to the general public. And then similarly, we have the weather-based advice. Like, for example, it tells you, is there a possibility of disease coming up or not? So on what you're seeing on the right side is the farmer saying that if this is the date today, then over the next few days, what is the possibility of disease? So 7 is severity rating. So that's in red. So that's telling you that on these days, there is a high likelihood of disease occurring due to the weather conditions. Whereas the days before that is not, maybe much of a problem. So so it's like the next few days is risky. So this is the date in the bottom. So this is November 29, November 30, December 1. And then if you go further on, then it's not too risky. So in the near term, there is a high chance of disease. Be alert. If you see something happening, immediately spray your field. So this way, that's very much helpful to the farmers that way. Then similarly, planting status and yield prediction and things like that. So it tells like if you click on this and ask for the advice, it says you're okay for planting today or not. And same thing, later on all this text is converted to Hindi, Punjabi, different languages. And right now it's very textual and farmers don't like text. That's what we realized. So it has to be very pictorial. That's why we have now remade this app to make it very pictorial in that sense. And then other information about it. And the final part of it, just in a couple of minutes, is that we have to bring market data into it, because finally, end of the day, you help the farmer increase the potato yield and everything. And then if he finds out there is a glut in the market, he has no rate. I mean, he gets no return. So how do we find out, what is the current rate for various crops, so that we can even advise the farmer that maybe don't plant potato this time, or plant 50% potato and plant 50% lentils or something else, like cauliflower or lettuce or peas. All of these are cold weather crops that match potato, that can go complementarily with potato. So these are other information we can give farmers. So based on that, we are collecting lots of market level data about what are the minimum maximum prices, retail prices, what is the availability of cold storages. Supposing you have excess potato, then where will you store it? So that, and this is all GPS enabled. So a farmer, when he searches for this, it tells him nearest to him what are the available cold storages, what are the prices available. So these are some of the things also that we are working on. But market data is a lot more complicated than scientific data. So market data is very fluctuating. There is no easy modeling to do for it. And there are lots of, once money is involved, there are lots of other factors that are out of your hands, starting with the fact that people are very dishonest. So it's very difficult to get accurate and, reliable data. But this is also something that we are trying out. So this is just a summary of what I discussed on Farmer Zone, where we have this, Q&A chat features for the farmers, so that they can also type in their questions and get community support. Then Market Zone insurance advisories, cold storage information, and then disease detection model that we have developed. Then we are working on enhancement of the advisories and other, revenue prediction models. This is all quite, very challenging problems, revenue prediction. Something we are working on initially. And then other things like what is the cold storage information, availability of certified seed suppliers, availability of insurance. So this is all information we are putting in the app. The point is that when you are doing data scientific activities, it has to be complemented by all this kind of information as well if you want to sell it to your customer. Because he's not interested in your fancy algorithms alone. The customer only wants to know what benefit am I getting in the end of it. So in addition to all the algorithm part that actually we realize is very valuable, the farmer doesn't care for it. Although we know that it's all running on the algorithms, but that algorithm is all under the hood. So he's only going to see what's outside the hood, and he wants to know, in the end of the day, what advice are you giving him and what benefit are you giving him. So this is something I felt is, important to be conveyed to all aspiring data scientists to be, very thoughtful about these aspects. So that's the end of my talk. I can take any questions on chat or live. So how can we help farmers at ground level using remote sensing, GPS and data science? Well, one of the big uses of remote sensing, usually when people talk about remote sensing, it means either satellite data or data from UAVs, which are flying at a very great height, not the ground level UAVs, but these almost like aeroplane kind of UAVs, which fly at a large height. And usually these have been used for either, so from you can get these satellite data images now from various sources like the Sentinel satellites and all of that. Some of them are paid, and the free ones also have reasonably good resolution. And by using a combination of image analytics on these remote sensing data, that is the image data, as well as trying to bring in weather data, you can try to do some kind of predictions for farmers on the ground, which tell them how, about their yield prediction or things like that. Now, normally I have tried to stay away from remote sensing data for the simple reason that in academia, and in India, considering two factors. One is in India, farmers are poor. Number two, in academia, we are poor. Okay. And the point is that remote sensing stuff is the stuff that can be directly tackled by seed companies and all who have huge amounts of money. So it's very difficult for us to contribute something to the space. So the space is very useful. The question is useful. Remote sensing is useful. Data science is useful. But there are big guys working on it already, and it's going to be difficult for me to contribute something beyond what they are doing. Whereas if I talk about this ground level sensors, the big companies don't have the manpower to go around installing sensors here and there. So when you talk about low cost technology and all, this is where academia and, especially in the Indian context, we are able to play a role where we can contribute and say that, I'm doing something beyond what others are doing. When you talk about remote sensing, it becomes a little difficult. That there are lots of people working on it, lots of experts and people with lots of funding. See, the main was, I felt there are, one is the data science itself. I'm sure there are other faculty talking about it, and I've done a bunch of data science and machine learning, and I've applied it to various domains, including material science, not at all agriculture. And I feel that, some take home messages from data science is first, you need good data, because it's very difficult to do data science without good data. The second is you have to be very honest, because one thing that happens to aspiring data scientists is that you see lots of these research publications, people are writing papers and all, you get influenced. You think that what they are saying is correct, and when you analyze data, you try to interpret it in a way that matches what other people are saying. But the whole idea of data science is you should not have to have any preconceived notions. You should be able to derive the messages of the data from the data, irrespective of what anybody else told you. And I feel that's what I call as the honesty, that you should be confident enough. I mean, you can interpret data, and many times there are goof ups, you make mistakes and all. So I'm not saying you have to go around challenging everybody based on your conclusions, but you have to be very open-minded. You analyze data, you figure out that there is something and it's contrary to what many people are saying. You work on it and make sure that you have either come up with a new conclusion or not. But don't start with a preconceived notion that everybody else is saying something, and so I'm trying to interpret the data in a way that matches what other people are saying. If you do that, then there's no point in being a data scientist, because what's the use of the data? You're finally putting all the effort to simply agree with what somebody else is saying. So that's, I think, just another important thing about the data science part.
Thank you very much, sir.
Thank you very much. Thank you for your kind attention.